Okay, good evening again. This is Professor ProfDavidJDelosReyes, okay? My topic again for this morning will be a long video format discussion, and this will now be alternating current circuit, and we are now on lesson number 17. So for those of you who are following my alternating current circuit discussion, this is now lesson number 17. This is one of the so-called important topics under alternating current circuit. This is a board exam topic. Okay, if you will understand my discussion for tonight, I am sure you will pass your board exams. Okay, let's proceed. Our lesson for this morning will be a long video format discussion, alternating current circuit, and this will now be lesson number 17. We are now through with the series impedances. We are now through with the parallel impedances. For tonight, this will now be the worst case scenario, that is the combination of a series parallel combination. It's a combination. There could be two components in parallel, which is in series with some other components maybe. But for tonight, I will just give you three impedances. Z1 is in series with C2 and C3, in which, for the given example, C2 and C3 are connected in parallel. So this portion of the circuit here is parallel, okay? And the series equivalent, or the parallel equivalent of this is connected in Z1. That's why our topic for tonight will be a series or a parallel series combination. Okay? So at least you know how to evaluate a series impedance and a parallel impedance if they are connected in parallel. If they are connected in series, you know how to do it. You just add it, right? If they are connected in parallel, if there is only two, okay, you could take 1 over C1, 1 over C2, or just simply if there are three impedances in parallel, use the admittance method. It will be the simplest solution of a parallel for taking the equivalent. Okay, let's proceed. I will give you an example problem just to illustrate how to solve a series parallel combination. Okay, we are given an AC circuit. This is the AC circuit. This is a symbol for alternating current. The applied voltage will be 120 volts. Okay, I will now place the angle to be 0 degrees. As always, the applied voltage is actually the reference vector or the reference parameter. Okay, it got an angle of 0 degrees. So if you try to draw the vector diagram of the voltage, it is horizontal line. This is the voltage, and if you try to place the angle of that one, it is always at 0 degrees. Okay? That's the meaning of this. The frequency is 6 Hz. For tonight, we do not even need the 60 Hz because I've given you some other values in which you do not need the value of the frequency. I just put the frequency to be 60 Hz. Z1 is 3 plus G 4 ohms, inductive. Z2 is 1 minus G3, this minus. So this should be a motor load maybe, and this is a capacitive load because this is minus. The third one is C3, the value of 6 plus G7, it is plus. So this could still be a motor load maybe. So meaning to say this motor and capacitor are connected in parallel, and the combination of this, if you try to compress it into one, is in series with C1, so it could either be a motor load maybe. Since the solution of the problem is a little bit long, just to illustrate on how to bring out the computation, okay, I will just ask 5 unknowns for the given problem. So for the given problem, Z1, C2, and C3 are given. The applied voltage is given. What I am only asking is that find the total impedance of the circuit. Okay? Total impedance, meaning if we try to compress this one, okay, what will be the single equivalent impedance? Okay, the capital letter Z with the subscript T, meaning total impedance. If we try to compress this one as a single impedance, what will be the total value? Next one, what will be the total current? If we try to compress this one, of course, it will draw a current, right? So I am asking what will be the value of the total current, right? Next one, what will be the current consumption of Z1? The current passing through Z1. So I am asking for I1, right? Next one, I2, the current passing through Z2. What will be I2? Right? Last one, what will be current I3 equal to? Okay, I will try to erase this one. I will try to erase this one. Okay? So we are given C1, C2, C3. We are given the applied voltage. C1 and C3 are in parallel. The combination of these in series with C1. I am asking for the total value of the total impedance of this. Okay. The total current drawn by these three impedances. The current passing through Z1, which is designated by I1. Take note of the subscript. 1 refers to C1, 2 refers to C2, and 3 refers to C3. What will be I2 also, and what will be I3? I could ask for the true power, apparent power, reactive power, and power factor, but the concentration for the meantime of the concept for this lecture will be C total, I total, I1, I2, and I3, because the other ones in which I would like to ask will be just an easy ones already. So we will just concentrate on the total impedance and the currents coming out from every parameter on the circuit. Okay, let's proceed with the solution. If we try to analyze the circuit, since the combination is a series parallel, okay, we will try to start in here. We try to compress this C2 and C3. We try to compress this one. And for my solution, I compress C1 and C2, C2 and C3 as Z4. Okay? I will compute for the value of C4, in which the C4 is the single equivalent of this. Okay? To compress C2 and C3 to get C4, since they are in parallel, I will use the so-called admittance method. So I will try to convert first C1 or C2 and C3. They are in rectangular. I will convert them first to polar. Okay? So you should bring out your calculator. This 3 here and this 1, 3 over 1. Take the ratio, press the arc tangent. What will come out will be 71.56 degrees. Negative, because this is negative. Take the cosine of this. Divide that cosine value to 1. What will come out should be 3.16. The magnitude of C1. Okay, so we are converting from rectangular to polar. The unit is ohms. Right? For C3, it is 6 plus G7. Again, the solutions, you should not bring out the solution of this. You just perform this on your calculator. 7 divided by 6, take the arc tangent of that one. It should be greater than 1 because 7 is greater than 6. So this should be greater than 45 degrees. What comes out is 49.38 degrees. Take the cosine of this. Divide that cosine value to that 6. What will come out should be 9.22. Okay? So we now change C2 and C3 to what you call this polar. Right? Let's try to compute for, we now know C2 and C3 in polar, right? And by definition, admittance is actually the reciprocal of impedance, right? So if we know C2, we could compute for the Y2 of this one. So Y2 will be 1 over C2. This should be 1 over 3.16, angle negative 71.26 degrees. Take note of the sign. You just made one sign, it's all wrong. Okay? negative 71.36 degrees. 1 divided by 3.16 will be 3.316. We raise this up, it will now be plus, right? 71.56 degrees. Okay, converting this to rectangular, take cosine multiplied by the value of 0.316, it will be 0.1. Take the sine of this multiplied by the magnitude 0.316, it is 0.3. It seems you are having a right triangle, right? Right? It is just something like that. You are computing for this and this, right? We are given the magnitude. Okay? So it seems this is 0.1, this is 0.3. It's just like that, right? For Y3, we know C3 in polar. So admittance number 3, if we try to convert it to admittance, so the value of C3, 1 over C3. 1 over 9.22 over 49.38. So this should be 0.108. This is plus, right? We raise it up. This should be negative 49.38 degrees. Converting to rectangular, cosine of this times 0.108, 0.0703. The cosine of a negative angle is still in the first quadrant, this is still positive. And take the sine of this times 0.108, it will be 0.0819, but it should be negative. This is because it is negative. And computing for the total admittance, we are now compressing this one in terms of admittance. That's why I place it here. Y4, the single equivalent of C2 and C3 will be Y2 and Y3. Okay, so this is rectangular. Okay, this is the rectangular of I1, this is the rectangular of Y3. Compressing this one, combining real to real, imaginary to imaginary, what comes out for the magnitude of C4 will be 0.2767 angle 52.01 degrees. Okay, mho. The unit is mho. So we now know the single equivalent admittance of this. So to compute for the value of C4, just take the reciprocal of the admittance. Right? That's the trick. Okay? We know Y4 already, the single admittance of this one. So to compute for its equivalent in terms of impedance, we will just take the reciprocal. So this is 1 over 0.2767. The angle is 52.01 degrees, right? So 1 over 0.2767, this is 3.61. Okay, this is 52.01. We raise it up. This should be negative 52.01 degrees. So the single equivalent of C2 and C3 is 3.61 angle minus 52.01 degrees. It's negative. So the capacitive load is more powerful than the motor load because this is negative, right? So we now know C4. And converting to rectangular, cosine of this times magnitude, that will be 2.22. Sine of this multiplied by 3.61 will be negative 2.845. Rectangular form, the unit is ohms. Okay? So, this C4, this compressed equivalent of C2 and C3 is connected in C1. So, okay? So, use your knowledge on how to compress two impedances in series. It is just the sum, right? So, C total now will be the compressed equivalent of C2 and C3 plus C1. So, we are on the series circuit portion of the topic. The first one is actually the parallel portion. Okay? So, computing now for C total, it will be C1 plus the compressed equivalent of C2 and C3, which has a very long solution. Okay? And in terms of rectangular, that is 2.222 plus 2.845J. Okay? 3 plus G4. Z1 is 3 plus G4. 3 plus G4. Okay? C4, the single equivalent in terms of rectangular is 2.222 minus G2.845. Again, this is algebra. Compress the real part, add the imaginary part. Okay, what comes out will for the imaginary part for C total will be 5.222 ohms. Okay, and the imaginary part This is plus 4. This is minus 2.8. So it should be a positive value. What comes out is 1.8155. So meaning to say, if we try to draw the, what they call this, impedance, the single equivalent impedance of the given series parallel combination, it will be something like this. Right? This is R, this is X of L, and this is C total, R total, XL total. R total is actually this one. XL total is this one. Okay, the compressed value of this, if we add it vectorially, okay, imaginary part, real part, so use the cosine value or the sine value or use the, what they call this, Pythagorean principle. What will come out will be, C total will be 5.348 angle 12.47 degree. The unit is ohms. So meaning to say, the single equivalent of this is actually 5.348 angle 12.47 degrees, and the angle is plus, so meaning the overall inductive reactance is plus, so meaning to say it's a coil. The motor loads are actually more powerful than the capacitor loads. This is plus. So this is the vector diagram. R total, X total, this should be C total. This angle here is 12.47 degrees. So we now know Z total. Okay? Since we know C total, we know the total applied voltage coming from the utility line. Okay? Therefore, I total will be the applied voltage over C total. Use your knowledge of the so-called simplification of division of what you call this complex numbers. The value of E in terms of polar will be 120 angle 0 degrees. Like what I said, the voltage is always the reference vector, right? And the total impedance, as per our computation, which is very low. That's why initially, okay, just be careful on the sign here. Just one wrong sign, all this will be wrong, right? So this should be 120 angle 0, 5.348 angle 12.47 degrees. We are dividing two complex numbers in terms of polar. There's no problem, right? Magnitude over magnitude. So this should be 22.438. 0 minus 12.47, this will go up, right? Negative 12.47 degrees amperes. What's the significance of this negative sign? The power factor will be lagging, right? Because X of L is the overall in the reactance that comes out. It's a plus, right? So it's a lagging power factor. Maybe the utility company is still mad at you because your power factor is lagging. Okay? So we now know the total current. And from the given figure, this total current passes through Z1, right? So I place it here. I1 should be equal to I total, and the value will be the same. Right? The magnitude is 22.43, same as this. Because as you will see it, current total is the one coming from the utility line, right? It passes through Z1 with no other things on its side, right? It's complete Z1. So I total is actually equivalent to I1. 22.438 negative 12.47 degree ampere. Or how could we compute for the value of I2? I2 and I3. Okay? The addition here and subtraction is actually vectorially. You cannot just subtract 12 minus 4. Okay? Vectorially. So use your knowledge on how to convert from polar to rectangular. Okay, let's try to compute first for the voltage V1. Let's try to compute for the voltage across this. Okay, across Z1. We know the current passing through Z1. We know Z1, so we could compute for the voltage across Z1. And the voltage across Z1 will be I1 times Z1. Okay, perform complex operation, right? 22.438 angle negative 12.47 degrees. And the total value of impedance of Z1, what's Z1? Z1, if we try to convert it to polar, I converted it already. 3 plus G4, 4 divided by 3 will be 1.33. Arc tangent, that's more than 1, so this is 53.13 degrees, greater than 45 degrees. Take the cosine, divide that to 3, what comes out will be 5. Or you could use Pythagoras, 3 square plus 4 square, 9 plus 60, square root of 25, the magnitude will be 5. So C1 will be times 5, angle 53.13 degrees. Try to multiply using your knowledge of complex simplification. Magnitude to magnitude, that 112.90. Negative to, you add the, what do you call this, the angle, right? Negative 12.47. If you are multiplying, you add the angles. This negative, this plus, but this is bigger, right? So what comes out for the angle of B1 will be 112.19, angle 40.66 degrees volts. Okay, this is the simplified vector diagram of the voltages. What we have computed, the B1 is this one. Its angle with respect to the horizontal is 40.66 degree volts. Because the vector sum of B2, okay, plus B1, okay, is actually equal to the applied voltage. Okay, later on, I will go back to this. So we now know B1, right? So B2, we now know the voltage across this. So to get the voltage here, we will get the applied voltage minus the voltage here, right? So I place it here, B2 will be the applied voltage coming from the utility line minus B1. 120 angle 0 degree minus 112.19 angle 40.66 degree volts. This one. You subtract this one vectorially. So try to convert these voltages to rectangular. 120 angle 0 degree is actually 120 plus G0. Cosine of 0 is 1, 1 times 120 will be 120, sine of 0 is 0, 0 times 120 will be 0. So 120 angle 0 degree will be 120 plus G0. Okay? 40.666, this is plus. Take the cosine, multiply 212.19, this is 85.1, 40.66, take the sine, multiplied by 112.19, that will be 73.1. The operation is subtraction, right? Okay, so for the real part, it should be 120 minus 85.1. That will be 34.90. 0, this is preceded by minus, right? So this J here will now become negative J 73.10. Okay? And if we try to convert this one, meaning to say B2 will be something like this. Right? It's downward. This is 34.90 and this is 73.10. Right? To take the magnitude, as usual, use your knowledge of trigonometry. Take the ratio 73.10 divided by 34.90, that's almost 2. Okay? Then press arc tangent. 2 greater than 45, so the angle should be greater than 45 degrees. What comes out is 64.47 degrees. Why negative? Because this is negative. Okay? Take the cosine of this, you divide that to 34.90, what will come out will be 81. So the voltage across Z2, and which is actually equal to C3 because they are in parallel, right? The voltage of B2 is actually this one here. 81 volts and the angle is negative 64.47 degrees. This is horizontal, this is negative 64.47 angle. So actually the vector sum of B1 plus B2 is actually equal to E, which is 120 volts. You are adding two vector quantities, okay? E 120 degrees is actually the vector sum B1 plus B2. Okay, so you could not just add the real part with the so-called imaginary part. You separate the real from the imaginary. Okay, so this is very important. Right? So what comes out now will be, we now know B2. B2 will be, or I2 will be equal to B2 over C2. We know the voltage across this to be 81. you divide that to C2, what comes out will be, the value of I2 will be 25.63 degrees, 7.09 degrees. Okay? And the value of I3, same voltage. B2 and B3 are the same, so we now know the voltage across them. So I3 will be B3 over C3, in which B2 is equal to B3. What comes out will be 8.78 angle negative 113.85 degree ampere. Okay, so this is the magnitude of I2 is 25 amperes. Okay, it got an angle. And the magnitude of I3, it got a magnitude of 8.78. Okay, let's try to check if our currents are correct. Because if they are not correct, our solutions are all wrong. So how could we check the validity of our answer? You try to add I1 should be equal to I2 plus I3. If I1 is equal to I2 plus I3, okay, if they are equal, we are correct. So I place it here as a check. I1 is equal to I2 plus I3. That's why I converted already the two currents, I2 and I3, to rectangular. Because I am preparing for the so-called vectorial addition. So I2, this will be the rectangular equivalent. I3 will be, this will be the rectangular equivalent. And if we try to compress, simplify this one, what will come out for the value of I1 is 22.4, right? And the angle is negative 12.5 degrees. It is almost same as this one. Okay, except for the so-called accuracy-wise, of course, we are using our calculator, right? So this is 22.4 as per I1 is equal to I2 plus I3. And originally, we converted I1 to be equal to 22.43, negative 12.47 degrees. So we are correct, right? I1 from this is actually 22.438 or negative 12.47. And as you check, we add the value of I2 and I3, and what will come out supposed to be is almost equivalent to this. It is approximately 22.4, negative 12.5 degrees amperes. Magnitude is almost the same except for the accuracy. The angle, negative 12.5, this is negative 12.47. They are correct. So all these portions of the solution is correct. So if you are on the board exams, this is correct, this is correct, this is correct, this is correct, you got 100%. Okay? That's how they check the papers on the board exams if you are having to perform your solutions on the board exams. Okay, that's it, guys. That's the way how to pass the board exams. You should check the validity of your answer, because if I1 is not equal to the I1 in your checking, you are wrong. Okay? As per magnitude, this is 22.4. Okay? This is 22.4. The angle is negative 12.47. This is negative 12.5. It is correct. So all portions of the solution is correct. Okay, so for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJDelosReyes. If you want to share it, please click share. Okay, I am telling you this one. For those who are following my alternating current circuit long format video discussion, try to watch my video. You will learn something from it, I will assure you. Okay, good morning from Los Angeles. This is Professor David J. De Los Reyes.